Are primes chaotic? This topic has always been a hot research direction. Primes are generated by a definite sieve method, but their distribution shows strong randomness. It is this contrast charm attracted generations of mathematicians to devote themselves to it. We randomly remove some numbers from the natural numbers, and then use the sieve method to remove composites. The resulting distribution seems to be random. Deterministic rules can produce randomness. This should be the phenomenon of chaos. A recent study provides explicit numerical indicators for the chaotic properties of prime numbers. This study uses a method called symbolic dynamics. It explicitly gives the prime number distributions, Lyapunov exponent, and topological entropy. A positive Lyapunov exponent indicates local sensitivity, and topological entropy is exactly between completely deterministic and random, indicating that the prime number distribution is typical weak chaos. The basic idea is to apply the dynamic form of the sieve method. It represents the sieve action as a symbol sequence, and successively perform the sieve of primes, forming a periodic sequence of symbols. Eventually, this sequence approaches really our infinity. According to the Mises theory in symbolic dynamics, these symbol sequences can correspond to a logistic mapping orbit. We can examine the mapping parameters corresponding to these sequences on the bifurcation diagram of the logistic map. When the prime number is infinite, the parameter corresponding to the symbol sequence approaches 1.5437. The key point of this study is that we used the method of symbolic dynamics, construct the isomorphism between prime number and the logistic mapping orbit. We can use the mappings to study the prime number distribution problem. The position with the orbit less than 0 is a prime, denoted as L, and positions greater than 0 are composite numbers, denoted as R. In this way, we obtain a prime number distribution. The reverse isomorphism between chaotic orbits and prime distribution is the key to applying such correlations. First, we compare the prime distribution constructed from chaotic orbits with the actual prime distribution. Positions less than 1.5437 are isolated even intervals. Only the position of 1.5437 is basically similar to the real prime distribution. After that, odd intervals appear. Only the position of 1.5437, only the point where they are to be merged, shows similarity in distribution. But this isomorphism has a fundamental contradiction. The prime density represented by the orbit is constant, while the real prime density is changing. This study further upgrades the mapping to a non-autonomous form to solve this problem. Then analyze the prime sequences generated by the non-autonomous form. The blue line represents the real prime distribution. The green line represents the distribution of the non-autonomous model, which is closer to the real prime number distribution. Compared with the self-made form and random model, there are obvious improvements. Then, the twin prime constant is reproduced. Using the non-autonomous dynamical model of twin primes, the twin prime constant can be perfectly reproduced. Based on the isomorphism between prime distribution, what new conclusions can we draw? First, it is the exploration of the twin prime problem. Using chaotic orbits, we can obtain the orbital density of twin primes. Then we accumulate the number of twin primes, which is to solve the integral. This leads to the conclusion that there are infinitely many twin primes. Note that this part is heuristic exploration, without strict mathematical proof. Then there is the addition of primes. Can be explored by coupling to chaotic orbits. To explore the Goldbach conjecture, the recommended tool is the coupled mapping lattice. Finally, we explore the Riemann zero. According to Hilbert-Polya conjecture, dynamical systems isomorphic to prime distribution. Its spectral distribution should coincide with the distribution of Riemann zeros. We calculated the eigenvalues of the non-autonomous logistic map. It is consistent with the previous Riemann zeros. The research paper also clearly explains the application of AI large models in scientific research. The greatest role of AI is to remove the isolation walls between disciplines, making interdisciplinary research easier than ever.